Welcome to our free GRE prep hour. My name is Whitney Garner, or Whit, either one. I live in Durham, North Carolina. For those of you guys looking maybe at programs at UNC or Duke University, you'd be right up the road for me. Maybe even NC State for my ag and veterinary folks out there. But I live here with my 3 crazy dogs, and right now the weather is finally starting to get nice and warm. So looking forward to taking advantage of all that North Carolina has in the summer. Lots of lakes and oceans and things to do. So hooray. Do me a favor, guys. Just go ahead and type in the chat window. I always like to hear where people are coming from. Where are you guys? Put it in the chat. Where are you guys? Nice, LA. Nice, Alex, LA. Oh, a few of you guys are in California. Am I the only East Coaster? There we go, Nicolina. Nice. Abby, you're right up the road. A couple of New Yorkers. Nice, you guys. Nice. Cool. Very cool. Well, we've got a lot to cover tonight. I'm doing a session tonight on a topic that is near and dear to my heart. It's one of my favorite things when I was studying for the GRE. It was one of my favorite things that I learned. And it's one of my favorite things to work with students on. It's a nice, fast way to get a lot of points on questions that could potentially be really hard or take a really long time. And so we're going to work on, Atlanta. Yeah, nice. Get them to the south. I need some more southers. So we're going to get going. I want you to absolutely feel encouraged to type in the chat window and let me know if you have any questions, anything that you want to pause and look at along the way. But without any further ado, we're going to be working on problems from the 5-pound book. If you have not gotten this book, this is a phenomenal resource of just a treasure trove of GRE questions. And many of you guys know that out in the GRE space, there just aren't a lot of questions available. But, you know, it's a good place. We can add to that. So you can get that directly from us or on Amazon. So here's what we're covering. We're going to talk about picking numbers, right? And so for those of you that have done any work with us, we're a big proponent of picking numbers for QC, for quantitative comparison questions, because that's probably the #1 strategy for dealing with QC problems. Pick a number, see what kind of answer it gets, pick another number, see what kind of answer that gets, and try to prove that the correct answer is D, that you can't tell. The thing is that picking numbers is great for QC, but it's just as great for the non-QC questions as well. So for discrete quant, where you're dealing with multiple choice or fill in the blank or choose all that apply, picking numbers and plugging them in is literally my favorite strategy. And I use it so frequently. It doesn't have anything to do with the specific content that's being covered. And we'll see tonight that they could test anything under the sun, and you can make it easier by picking your own numbers to plug them in. And so we're going to look at how the mechanics of picking numbers will work for our non-QC questions. But more importantly, how do we recognize when these opportunities are available to us going forward? So we're going to actually talk about 4 different scenarios, and I'll sort of line list these and we'll take away summary them together. But we're going to look at 4 different scenarios where you can pick your own numbers, and they're actually pretty easy to recognize once you've had somebody point them out to you. So what I'd like to start with is an actual QC question, right? Because oftentimes we're very easy, it's very easy for us to pick a question or pick a number for QC. So I've been pulling a few from various places. But let's try something like, and get your calculators ready if you don't have it. Let's try the following problem. I'm going to give you guys 1:20. What I'd like for you to do is send me your answers privately. So send me your answer. Use the little blue drop-down list. Send it to panelists as opposed to panelists and attendees. I'll get some time going, but let's try to take about 1:20 for this question, and then we'll talk about how you guys solved it. Still on mute. There we go. I was giving a little bit more time for folks to get me some answers. I've got answers from 7 of you guys, so great. Oh, that's okay. Abby, great question over in Q&A. You're going to look for little 3 dots that'll say chat, I believe, that you should be able to see the chat pop up. Let me see if I can send you a chat directly. Let's see here. Let me see if I can send, oh, that's what I'll do. I'll send it out to everybody, see if this pops up. Hi, everyone. Me and tech sometimes are a little. Yeah, you can. You can ask questions about all kinds of stuff. You're welcome to type it in. I'll leave some time a little bit later in class to talk about other stuff. Tonight's plan, though, primarily is to talk about how to handle the idea of picking my own numbers. So I've got a bunch of different answers. I've got some choices on A, some choices on B. I like it. How did you guys try and solve it? Type in the chat window, and you can type this out to everybody, panelists and attendees. Talk to me. What was something that you tried to do? See if we can build on what is something you guys tried to do. Yeah, okay, so use a calculator, start from 10, applying the discount. I like all that stuff, but starting with a number, right? So often it's a nice way to start with a number. So the price of an item after 5 consecutive 10% discounts are applied. All right, so let's start, right? If we started with an item that was $100, if we take 10% off, we lose $10. Our first one is $90. Then we're going to take $9 off. That takes us to $81. So we've got 1, 2. Let's take $8.10 off. And you can throw that in your calculator. Now, what I'm looking for, though, is that same item, 50% of the item is just $50. So is this going to end up below $50? Ah, that's a good reasoning. That's a good reasoning. If I keep taking 10%, though, let's think about this for a minute, right? And I like what Papa is saying in there. That's great. If I keep taking 10% of this total, the amount I keep taking is less and less, right? So the first one I took off was 10. The next one I took off was 9. Then I'm only taking off $8. Then I'd only be taking off $7. So even after 5 of those, I won't be taking $50 off. So $50 of the price of the item, or 50% of the price of the item is $50. How much, though, is the item going to cost after I did 5 consecutive 10% discounts? So you could keep grabbing your calculator, right? And I would argue, go for it. You've got 81 minus 8.1, right? And so 72.9. And I'm going to subtract $7.29, right? And that'll leave me down. So there's my 1, 2, 3, 4. I'm down to $65.61. Look, I'm only going to subtract $6.56. I'm not going to get down to $50, which means be careful. I'm taking a lower discount in quantity A, but the price of the item after the fact is going to be greater. So we want price of the item afterwards going to be greater. You can think through the logic of this. I saw a couple of you guys like, well, here's the logic. But one thing that we can do, right? So when I think logic on the GRE, I often think algebra, right? Like theory. And algebra is working around unknowns. That's literally what that means. When you're doing algebra, you're working around things that you don't know. That's why we have variables. Arithmetic is the act of just crunching numbers. And in fact, arithmetic is theoretically and mentally less arduous. Right? So when we're doing an arithmetic, like any operations that are arithmetic, it doesn't take as much mental computing power. And that's why picking numbers, even in questions where there's theory, can be a really powerful way to not only solve the question, but maybe it's just to reconfirm the theory that you believe. Right? So that's all well and good, right? That's great for QC. The question is, could we do the same thing for a non-QC question? And the answer there is yes. So again, we're going to look at 4 different types of non-QC questions that we can do this same idea of picking numbers for ourselves, right? So when it comes to, so when can we pick numbers? So the first one we're going to look at is, it's going to feel a lot like a QC question. And so I like to call these the must be true theory questions. Okay. So must be true theory questions are the first area of attack that we're going to see in picking numbers. So take a look at this problem. I'd like to give you a minute and a half just to get started. Now, this is a pretty big, hefty problem, but I'd like to get you at least on the way towards thinking about how you'd solve it. No big deal at all if you're still working. What I'd like for you guys to be thinking about is, what is it? And I got a great answer in the chat window, by the way. Somebody was like, oh heavens, I don't know, is it? Right? So what is it about this problem that makes it ugly? Well, if I'm going to try and do this problem with variables alone, leaving everything in the shape of variables, and I see language like which of the following must be true, I know that the GRE is trying to test a theory, that there must be something that's true about these, various fractions that would make these, change things when I've got exponents and the relative size of an exponent. So instead, what I might do is just plug something in, right? So pick a simple value for things like A and B, and then that could make my life a little easier. Now, there's a lot going on here. So let's start from the kind of uglier piece, the 1 over B. Let's pretend that B is 2, a nice simple fraction. So I've got 0 is less than something, is less than 1 over 2, is less than 1. And so now I could make A anything I want. I'll pick something kind of simple. I'll go with 1 over 3. Why not, right? Everything up here is just squared, so that's easy enough to find. So I need to remember that 1 over 3 is A. B is just 2. So now I'm going to go through each of these and try and take a stab, which is going to be bigger. So all of the places where I've got A, is it the fact that 1/3 squared, right, is bigger than 1/3? Ooh, well, no, 1/3 squared is 1/9. It's not bigger than 1/3. I don't have to test anything else. I can stop there. I can stop there. Well, in B, I know that B is bigger than A. The question is, let's see, is A, 1/3, bigger than 1/3 squared? And it is, because 1/3 squared is 1/9. And B squared is 4. No, that one fails. And so we can follow this same exact technique. It's almost like we were trying to prove D in QC. We're trying to break each answer choice to show that Given the numbers I picked, it's not going to work. So what I'm going to do is just keep plugging in. Now, if I get more than one that shows up as must be true, I'd have to pick a different set of numbers, right? But you can continue to move through all of these, right? We know that a squared is not bigger than a. We saw that in answer choice A. So use that knowledge to eliminate any other answer choices that would be taken out by that. I also know that b, which is the number 2, is not going to be smaller than either of my fractions. And so the answer has got to be E. I could prove it, but I don't have to. Here, b squared would be 4, b would be 2, a is 1/3, a squared is 1/9. If you're comfortable with the theory of what happens to fractions and numbers greater than 1 that are squared, great. I am, but I still feel better plugging numbers in because I think I can move faster without mistake. Right? Because when I'm trying to move quickly and keep a bunch of theory in my mind, I often drop the ball. Right? I'm far more likely to make a careless mistake. And so what we're looking for, a really common way that the GRE is going to let us pick numbers, is to think about which of the following could be or must be true. Right? And so just so you can try one more out, let's try one that's maybe same sort of idea, but a little bit different. You can even do these in you choose multiples. So let's try it from this one. I'll take about a minute and a half, let you kind of chew on it, and then we'll move on to the next type. All right. Oh, I think I did. Sorry, did it come back up? Sorry, I don't know how it disappeared. Did it come back up? I am terrible at tech sometimes. Oh my goodness. All right, let's try it again. I'll give you guys another, how much? Let me see. When did you guys run out of that? Let me give you guys another 35, 40 seconds. Is that okay? There we go. Let's see. That'll be open in the right place. All right, there we go. Sorry for the mix up with the slide, but how do we do it? What can we do for something like this one? What'd you guys try? Yeah, thinking about powers, right? Thinking about powers. That's fantastic. Right? Like, I know that when I raise something to a power, I want to think positive and negative. And for sure, you could totally do theory, right? There's nothing wrong with doing theory here. I just like to throw numbers in as well to confirm, right? Just to confirm. All right, so what we've got here then, right, let's try if they were both positive. Right, let's imagine they were both +1, +1. Then the first one would work. The second one would work. Ooh, and so would the third one. So clearly I have to pick something different. Let's imagine they were different. Let's pretend it was -1 and 1, right? If it was -1 and 1, then the first one would no longer be true. The second one would be, though. And we can use theory here by moving these pieces around if we want to prove it, right? X squared equals y squared by adding that y squared to both sides. So we can trust it in that case. We can do the same thing with the third one. If absolute value of x is equal to the absolute value of y, that would be true because if we square them, they're still equal, so their absolute values would be equal. So beautiful, B and C. So you can use a combination of plugging in values and thinking about the theory, using that to prove it to yourself. So in many ways, what I think of when I think of these plugging in numbers, proving the theory, is that you're going to pick some different numbers. What you might end up with are multiple answers that you have to try a few cases, right? So you'll be ready to try a few cases just like you would on QC. It's the exact same thing as you would on QC. Okay, so our first type were the must be true theory questions. Yeah, no, that's a great question. That is a great question. Does anybody have an idea? What is it in the language of this problem? Of either of these, in fact. What is it about that language that might say, hey, hold on, you're going to have to try more than one. You're going to have to prove. What do you guys think? Yeah, so there's a big difference between must be true and could be true. Could be true would be me plugging in the one example and trying to find any one of them that would work. Must be true means I need the one that would work in all cases. And so I'm going to have to try a couple of cases for those types of problems. And this is going to be very unique. So I love this question. This is the recognized piece of it, that I'm looking for a must be true or could be true, or which of the following must be false, or which of the following, or must be even, or which of the following must be odd. Which of these is an integer, which of these is will always be negative. You're looking for that. It's like a proof. They're trying to ask you to prove whether the answer choice is always or never going to be something. And so you can use this idea of picking numbers for any of those and very much treat it like it's still a QC problem. Let's try another little bit different. Let's try, yeah. So we're going to try the second type. We'll talk about what it is in a moment, but take a look at this problem and let's look at how you would solve it. All right, so I got a couple answers. Keep sending me your thoughts if you haven't yet. What can you guys do on this one? What'd you guys try? I got a bunch of people saying B. Yeah, I love it. I love it. Let's try a number. Let's just throw a number at this stupid thing. Why should I have to work around X? I don't know what X is. X is, they're asking me about X in the problem. The X is still here in the answer choices. It means that this value of X persists. It doesn't go anywhere. So it shouldn't really matter what I choose for X because it sticks around. This is very similar to the must be true type of problem. The difference here is that I don't need to expect to try multiple numbers. What I'm going to do instead is I'm going to pick one number. The only reason why I'd have to pick multiple numbers is if I get multiple answers that give me the same thing. And that's not all that common. So let's start with, Alex gave me an example of 7, which is really nice because that would keep everything positive. So I've got 7, 1, and 19. And so I want to know what the average of that is. 27 divided by 3, right? The average is the sum divided by the number of terms. And so this is going to be 9. I'm going to now plug in, see if I can write that legibly. I'm going to plug in X, right, where I said X is equal to 7. I'm going to plug that into my answer choices. This would be 7, 9, just to prove it, 16, and this is way too big. And so my answer is, in fact, B. So this is our second type of pick numbers, plug in, and be smart. I like to call them smart numbers. This is my second type of smart number. The smart number here would be that you're trying to, you notice that there are variables in the answer choices. You see them there. And so what you're doing is plugging in for the variables in the answer choices. So your variables in your choices, there we go. We're going to try another example of it. Apparently I can't get this to open. I'm a mess sometimes. All right. Variables floating around the answer choices give us a good reason to plug in. Let's try. Let's step it up a little bit, shall we? Ooh, come back. Good luck. Wasn't it this one? Oh, wait, no, why is it not? Man, I'm a mess today. Hold on, let me find it. I lost your problem. I thought it was this one. Am I a crazy mess today? No, you're right, it's not. Hold on, I had it. Why did it go away? I don't know how I lost the problem. There it is, I found it. There it is. Thank you. All right, let me start your timer over. Oh my gosh. I promise in the second half of this, I will be less of a tech disaster. My PowerPoint's been a mess today. I'm gonna give you guys some of your time back. There we go. All right, so big kind of messy question. If we were going to solve it, we could flip it and move pieces around. But if you weren't sure about the variable rules, or the fraction rules rather, you could pick some simple values for these. You just don't want to make them all the same value, but you could say that A is 2, B is 3, C is, or like make them pretty so they cancel, right? Like A is 2, you can make C equal to 2. And then you can make D equal to kind of whatever you want. So you could call this 2 times 3 over 2 divided by 2 times, let's call it, we'll do a 3 again here, 2 times 3 over 2. This would be 1. They'd be the exact same things. And so I can plug in really quickly and see that, well, A times C, right, is not going to work. B times C is not going to work. But 1 over BD also not going to work. If I take this, A squared is 4 times 9 divided by C squared is 4 times 3. That's not going to work. But if I take A, 2 times B squared is 9 over C, 2 times D squared is 9, there's my guy. Now again, you can always use the theory. What I like about picking numbers is that when I'm stuck and the theory is sometimes something I'm not 100% sure about, or I'm not always clear about how to set up the expressions, especially when there's variables in the answer choices, then what I want to think about is, can I pick numbers to make it real? B is, where's it going? Oh yeah, it is 3. Oh yeah, thank you. Oh my gosh, thank you for the fix, Alex. So what do I have to do then? What do I have to do then if I wrote that out crazily? What do I have to do if D and E gave me the same answer? What do I have to do? Yeah, I have to try some new numbers. And maybe what I do is not repeat the same numbers again. So maybe instead I make C equal to, and I can make it kind of anything. Maybe I make C equal to 1 and leave D where it is. And so see what happens when I make C equal to 1. And so now I change this guy and that guy. And so now I get 2 times 3 is 6 divided by 1.5. And now I can plug it into both of these and see what I get. So 4 times 3 would stay the same. This is 12 up top. Down here, I'd get 12 divided by 3, which would not work. But now if I try A times B squared, which would be the same as this, so that's 18 up top. C is 1, D is 9, right? Or I think I did a little funky math somewhere. But I can, or think, oh yeah, which is 3, or which is my, what did I do? I did something kooky. C times D. Oh, you did? Okay, so let's back it up and try. Let's try your numbers. Nice. I just did crazy numbers, I guess. So I like that you guys picked numbers that were different. This is why you shouldn't pick numbers that are the same. C is 3 and D is 4. And then you get what? 1 times 2 over 3 over 3 times 4 over 1. So 2/3 divided by 12. Yeah, you could always turn them the other way around so you're not dividing by a whole number. But at this point, you can take the 2/3 times 1 over 12, or you can take 2/3 and divide it by 12 in your calculator and see what you get. Yeah. We can still tell that these guys aren't going to work. Exactly, 0.055. Those guys won't work. 1 divided by 8's not going to do it. And so now I have to compare these two again. So 1 times 2 versus 1 times 4. Down here we get 9 times 4 over versus 3 times 16. And so the 4 over 16, that's not going to do it, but this one will. Yeah. There's my correct division. Nice. And this is actually, yeah. Yeah, so if we get the same thing for multiple choices, we're going to have to try new numbers. Now, I will say that these where the variables are in the answer choices are some of the ones where, for obvious reasons, you have to be the most careful. Careful because of what you're picking to plug in. Careful by testing out the answer choices. So we'll try one more. And I'll make sure nothing moves. I won't touch it. So we'll try one more of this tape. So what do you guys think about this one? I didn't get nearly as many answers for this one. So how do you pick for this one? What did you guys try? How do you pick? Yeah, and so if you pick for Y, what are you going to pick? What did you guys choose for Y? What did you guys choose for Y? Nice, $10, right? Because that's a nice, easy way. If I've got, $5 oranges, if I make them, if I make the total of Y equal to $10, right, that makes it really nice. How much? So if Y is 10, each orange is $2. How many dollars do 25 oranges cost? They cost $50. So now I've got to plug in my Y is 10. 10 over 5 is not going to work. 10 is not going to work. 10 plus 5 is not going to work, but 5 plus 10 will. So a lot of times plugging in our own numbers, especially when it's like not always clear how to set up the relationships, can be a really effective way, an extremely effective way. And you could choose all kinds of stuff, right? I like if you choose, well, let's notice what happens. If you choose $5, so if Y was $5, so each orange costs $1. Right? And so, or right, did I do that? $5. Y is $5. And so each costs $1. And so the total cost of 25 would be 25. When I plug in 5, right, once again, I can cancel it out on all. Doesn't work. So sometimes throwing a number in when you've got this variables in your answer choices running around can be really, really powerful. Okay. So now this gives us two different types. The last two, I think you guys are going to like the most. They're my favorite too. But just so you guys can sort of follow on the list, these are where we are so far. So when can I pick numbers? I can pick when it's a must be true theory type problem. But in those cases, I want to be ready to try a few cases. They are very much like QC problems in that way. I can also pick numbers for variables in choices. So when I've got variables running around in the answer choices, I like to choose simple values, but be careful. You do have to plug into every choice just in case you get a duplicate. Just in case you get a duplicate. Okay, so this guy is one of my favorites. So let's try this one. Here you go. I'm going to give you the full 2 minutes to try this one out. So what's the story with this problem? Was this one easier, harder? I have almost no answers. In fact, I have one answer. Talk to me. Is this a harder question than the previous? Right? Decoding the question is so tough. Oh my gosh. How many of you guys are sort of considering variables and setting things equal to each other with some unknowns? Anybody? I'll take a +1 if you were. Yeah, didn't know where to start. Oh my gosh, didn't know what to do. Well, let's think about these relationships for a minute. Okay? So we'll just think about how these relationships work. Let's look at the number of tickets that each member sold. Right? So let's talk tickets sold by each team or each club. We don't actually know. We don't actually know. So let's make up some numbers. Let's be really lazy and really simple. What's a sample number? I'm going to go even simpler, Nicolette. I like 15 though because it's a common denominator. I do like 15 because it's a common denominator. But I want to know that the AV club sold 2/3 as many as each member of the chess club. So I want a number that I could take 2/3 of. So let's pretend, we can do this a few different ways. Maybe it's that the AV club sold, so I like, Nicolette's idea of 15 or Abby's idea of 30. If there were, let's say, the chess club sold, 30, that would mean that the AV club sold 20. All right, what about, I could have even taken this simpler, we'll look. But now the second piece talks about members. So the number of tickets sold by each club member, right, that's before, each member, isn't really related to the number of members, right? Because this is tickets per person. Now I'm talking number of members. So I'm going to make up some other numbers for this one too. So give me some numbers that would fit with this story. What are some numbers that would fit with this story about my AV club and members of the chess club? Nice. I love it. Ooh, I really love the simple 3 and 5, right? I see if I love yours too, but I love the 3 and the 5. So let's imagine that the chess club, these are pretty small clubs, right? Let's imagine the chess club has 5 people in it. That would mean that the AV club has 3 people in it. So how many tickets were sold by each club? So how many tickets did the chess club sell? Well, they had 5 people, and each one sold 30, so they sold 150 tickets. Nice. That's cool. And then the AV club, well, they have 3 members who each sold 20 tickets. That's 60 tickets. What fraction of all the tickets sold by the 2 clubs? Okay, so that's total tickets, right? So that's 210 tickets. What fraction of the total tickets were sold by the AV club? How do I find that? What fraction of the ticket? That would be 60 tickets out of a total of 210. Bing, bing. All right, this would be 2/7. There's my answer. My favorite of the picking of your own numbers problems are when they don't give you any real values. There are no real values in this problem. Notice everything is a portion of something else. Everything's a portion of something else. And so this is a big one. No real numbers given. Right? And pick what you want, right? There's not always going to be a variable there. You mean, well, we did do that. Basically, you wouldn't want to go backwards from the number of tickets sold by both clubs, because the number of tickets sold would be the combination of members. And oh, this was a hard question. This is a very hard question. Yeah. So no real numbers given can be your dearest friend, right? This plugging in numbers for a no real numbers question can make life really a lot easier. All right. Let's try one more of those. It doesn't just have to be multiple choice. It doesn't just have to be these DQ. It can also be fill in the blank. So what do you guys think? We can pick a number for this one too. We can pick a number for this one too. She's going to spend a fourth of her money on a textbook. So I could give her $4, but now I got this 1/6 floating around over there, and that's not so pretty. So maybe I take that common denominator trick and say something like $24. So let's say Devorah's got 24 bucks, and she spends a quarter of that money on a textbook. So she's got a textbook that cost her $6. So then she had left $18. Now she's going to buy a notebook that costs 1/6 of the price of this. So she's going to buy a notebook, right? Be careful, 1/6 the price of the textbook. So she's going to spend another $1 on a notebook, which leaves her $17. So the fraction of the remaining money is 17 out of 24. Take it nice and slow. Once you start to plug stuff in, take it nice and slow. Right? She spends 1/4, so she has 3/4 left. She spends a 1/6 of the thing that she spent before, right? The numbers can get turned around. So it's a lot easier for no real values given, right? Nothing, no. For fractions, they shouldn't round. They should be able to, you don't have to put them in your reduced form though. But if they're in a fraction, it needs to be an integer over an integer. Great question. We'll try one more, just so you can, the last one we're going to look at, we'll look at very, very briefly. We've essentially already done it, but let's try one more just so you guys can kind of get a feel. Let's try this one. Not a ton of answers in, but we can do the same thing again. So we've got a local outlet. They sold 3 times as many jeans as chinos. So let's say they sold 3 pairs of jeans and 1 pair of chinos. And they make twice as much profit for a pair of chinos. So I'm going to say that they make $20 per pair. And so they make $10 per pair of jeans. They didn't say anything else. So what are their total profits? Well, they sold 3 pairs of jeans at $10 each. And they sold 1 pair of chinos at $20 each, which means their total profits were 50 bucks. And their percent of their profits that came from chinos was 20 over 50, or 2/5. That's the same as 40 over 100, or 40%. Much nicer than trying to work through a bunch of like would-be systems of equations. So what I find is that most people's favorite is the must be true and this kind of family of no real values given, pick your own. No real values, pick your own. So the last but not least one is this idea of the variable disappearing. And so I want to show you an example. This is my favorite because you can pick any number you want and it never matters because it's just going to disappear. Totally going to disappear. We don't have to think creatively. So the variable disappears, the kind of problem where a variable disappears would be something like the following. And this is what I mean by a variable disappearing. Give the question a read. I love it. Abby just Googled chino for us. Yes, they're like khakis, basically, work trousers. So notice that you're given two variables. You're given the variable x and you're given the variable y. The variables are not in the answer choices, so they disappear in that respect, but you're not solving for them either. Notice it doesn't say what's the value of x or what's the value of y. You're not solving for those variables. So you were given these weird variables. You weren't asked to solve for them, but they disappear because they're not in the answer choices anymore. It means that we can pick whatever we want. Right? Whatever we want. And so what we've got is a story where it's like when x is divided by 10, there's a quotient, that's the whole number part, and a remainder of 4. Well, what's a number that when I divide it by 10 would have a remainder of 4? Well, 14 would. Right? So if x is 14, when I divide it by 10, right, 14 over 10 is 1, remainder 4. Y is gone now. X and y are positive integers. Yeah, I did that. Y is totally gone now. What's the remainder when x, 14, is divided by 5? The remainder is 4. And I'm done. They're giving you variables to make a problem, often number properties, seem more complicated. When in fact, the variables are just thrown in there in some ways to throw you off. And so you don't need the variable at all. It didn't matter what it was. You can pick anything under the sun. Yeah, for sure. You mean like how to solve this one or just what it means that a variable disappears? Yeah, so how to solve this one. And then I'll put one other example of like a variable disappearing so you can see it. When we pick numbers ever, we have to think about the rules that we've been given. So the first sentence tells us what x and y are. So it says when x is divided by 10, the quotient, so if I'm going to divide, let's say I divide the number 15 divided by 6. 6 goes into 15 2 complete times. And then there's this remainder of 3. Because 6 goes into 15, right? You could do the long division if you wanted to. It goes in there twice, and that's 12, with a remainder of 3. The 2, in this case, would be what we call the quotient, and the 3 is the remainder. So I need a value for x that when I divide it by 10, I get a remainder of 4. Right? So I'm trying to think of a number that when I divide it by 10 would give me a remainder of 4. So 10 divided by 10 would be a remainder of 0, and 11 divided by 10 would be a remainder of 1, and 12, okay. So if I took 14, excuse me, and divided it by 10, and we could do that in the division, that goes in 1 time. Yep, there's my remainder of 4. So in my story, x, I picked the number 14, and when 14 is divided by 10, the quotient y is 1 with a remainder of 4. Yeah, I proved that. So if x and y are both positive integers, yeah, I checked that. That's true, they are. What's the remainder when 14 is divided by 5? Because remember, now I'm subbing for x. So what's the remainder when the value of 14 is divided by 5? And that's all I have to do now. That's all I have to do. And you could have picked a different number. For example, let's say you thought, oh, well, I know 24 divided by 10 would go twice with a remainder of 4. What's the remainder when 24 is divided by 5? It's 4. It's the same remainder. And so what we're doing is plugging in, yeah, of course. So one of the things, I'll show you one other example of this. I find that it can be really helpful. This, the fact that it entirely disappears means a lot of the time that we would have thought that we were going to have to work with crazy rules, but we don't. We don't have to work with crazy rules. It's actually really, really simple. You can use it to help sort of prove the answer to something to yourself. So for example, yeah, of course I certainly can. Yeah. I'll walk back through, I'll show you some examples of them before we leave. But notice that if x is negative, there's a variable. What is the median of this list? I'm not solving for x, and the variable isn't in my answer choices anymore. They gave me a variable, and then it just like disappeared into thin air. I didn't solve for it, but it just went away. And so that means I could pick whatever I wanted. And so all I need is a negative number. So I'm going to say x is -1. So my list would be -1, 3, 7, 11, and 20. My median is 7. Theory could help me there too. That's fine. But I think it's nice to be able to just plug in a number every once in a while. You're like, I like answer E. Yeah. You want to try a really doozy one? I'll give you one more. I know we're over, but I'll give you one more doozy. Yeah? Okay. All right. Here it comes. Hold on. Something else, guys. Now, the fun thing, again, this kind of smart numbers, this kind of plugging in, doesn't have to be a DQ specific, like a multiple choice answers. This can also be fill in the blank. Here we go. Let's see if I can, there we go. It wasn't opening correctly. Here you go. Here's the last one we'll try. All right, I got a couple of answers in. People sort of being like, wait, is it 0? Is that real? Yeah, so notice what we've got. The remainder when this number is divided by a single digit integer m is positive. Ugh. And as is the remainder when 120 is divided by single digit integer n. So if you know that you can be comfortable picking numbers, like, hey, there's variables here. If m is bigger than n, what's the remainder? I'm not solving for m and n, so I can pick whatever I want. You can start to think through numbers. But if I divide 120 by 1, that won't give me a positive. There won't be a remainder at all. Neither when it's 2. It's divisible by 3. It's divisible by 4. It's divisible by 5. Man, it's divisible by 6. It's not going to be divisible by 7. That would give me a remainder. So that's one of the numbers I could pick. So if I went 7 into 120, I don't have to find the remainder, right? I know that it's going to have one, but if I wanted to, I could prove it, right? And so I know that this is going to end up with a remainder of 1. So 7 works. And then the other thing it wouldn't be divisible by, we know it's not 9. And so I could, prove it to myself, but again, we don't have to. And so this is 3 and with a remainder. So what's the remainder when this number is divided by, well, m has to be the bigger one. So 9 minus 7, there's 2 of my numbers that worked. The remainder would be 120 over 2, which would be no remainder at all, 0. Sometimes people stall out on this one and don't think to plug in at all because people don't think they're allowed to plug in. And by plugging in, you can actually find the only 2 values that would work. But it wouldn't matter if there were only 2 values that would work. If it's written in this form, they have to give it to you in such a way that it would always be true that way. Megan, yeah, do you want to type a little bit more about why? About what's got you stuck? Yep, m minus n is 9 minus 7, which is 2. But notice what the question asks. What is the remainder when 120 is divided by that? Yeah. Just because you guys are so awesome. Literally, because you guys are so awesome. I'm going to trust y'all with a crazy problem. I lied. I said I was gonna do that last one, but here you go. I'm gonna trust y'all with this one. All right, so I know this problem looks crazy, but guess what? I can use whatever I want. They gave me x's and y's, but they disappear. I'm not solving for x's and y's. I'm solving for some big, crazy, complicated relationship. So I can pick whatever I want. I'm going to make x equal 1, and I'm going to make y equal 1, because they literally don't matter. They're going to go away. So I've got 5 minus 4 over 2 minus 1 divided by 3. Oops, I put that too close. 3 over 1 minus 2 plus 5. So I've got 1 over 1. That was easy enough. This is 3 over negative 1 plus 5. This is 1 over negative 3 plus 5. This is 1 over 2. I'm done. There's my answer. Later. I'm not multiplying my crazy stuff. I'm not like trying to simplify or move things around. I'm just going to plug in whatever in the world I could possibly want to plug in. I say this to my students a lot, so I'm going to put up the little summary. I know. Oh, so the only reason why this rule 2x doesn't equal y and 5x doesn't equal 4y, you would have run into it. They tell you that so that the denominators don't become 0. So you don't want to ignore those rules for sure. You would encounter them because these rules would make these denominators 0. But yeah, we do need to pay attention to the rules that are given. But given that 1 wouldn't hurt these relationships, I could pick the easiest silly thing I could possibly ever want ever. Right? And this makes my life a million times easier. So the GRE is not a math test. As much as they like to make it seem like it's a math test, it's not actually a math test. The GRE is actually a test of whether you're willing to be creative or comfortable being creative with math, right? With mathematical sort of concepts. And if you are, man, right, like you get, like, there's a great reward for that. And so here were the 4 types of number picking. So obviously you can pick numbers for QC. That's a massive, like, big deal strategy for QC problems. But you can also pick numbers for any questions that say must be true, right? Which of the following must be true? Must be even, must be positive, must be an integer. You can also pick numbers for the vast majority of problems that have variables in the answer choices. So you're going to choose simple values that fit the story. You're going to plug them into every choice and then try to see if any of them match your answer. The one that's, I think, the most popular is the no real numbers given, right? Everything is given as a fraction or a proportion or a percent. Right? All of this can show up in geometry, by the way, too. Every topic can be covered by one of these, right? You'll see them in every different content area. But for no real numbers given, everything's just relative amounts. You're going to pick whatever values you want that make the story fit and move through. There's not usually going to be a variable there, so you can pick for whatever you want. The variable disappears is the last one that we saw, where they introduce a variable. You never solve for it, but it's not in the answer choices. And so that one as well is another phenomenal place to pick your own numbers and throw them in. Yeah. So all of these are ways where you can take what would be more complicated theory in algebra and convert it into arithmetic. And it's my favorite techniques for the GRE. So we've got some upcoming classes. Come check them out. You know that you can take the first session of any of our in-person or online classes for free. So you should come try out even more of our strategies by joining us for one of our session 1s. But my name is Whitney. It has been a great pleasure to work with you guys this evening. Thanks for sticking around. I know we ran long, but there were some, glitches and snafus with slides earlier, so I appreciate it. Thank you all for your time. And I hope you have a wonderful rest of your Thursday, a wonderful week. Good luck studying for the test.